Here we are, most of us are at least awake. So welcome to this lecture. I will just hit this one button. Today, I will not go through the exponential smoothing as we did last week, but I just kept it in the slides for today because I did not update the slides from last week. If you like, I can shift it there, but I think the important thing is that it's there somewhere. So what we'll talk about today is basically the local trend model. And then since we got started on this week's topic last week, we will also get started on next week's topic this week. But today I did shift it into the slides. So we'll end up talking about some operators, so to get that part going as well. But first of all, what we've done so far is the exponential smoothing. But what we want to go to is, last week we did the so-called global trend models, and that was all fine. You had, at least, and I understand that, some challenges figuring out why do we actually want to do this. And I think the reason for having the time relative to the last observation rather than just an arbitrary beginning of time will become more clear after today. Not that I'm going to say a lot about it, but just because now it actually starts to make more sense. So what we did last week was to look at this structure of models, and we will actually look at the same model structure today. As such, n plus j equals f transpose of how many steps different forward or backward in time are we going, and then the current estimate of theta, and then plus some noise. And what we did last week was to write up an iterative solution for that, and we went through how do we actually get to that. So that is, you can say, the starting point for where we're going today. I will get back to the global trend model a couple of times, but could we do this locally? And that is an obvious yes. You could all scream it out loud, that'd be okay. But of course we can do that locally. What is the easy way of doing it? Well, the easy way of doing that is to just assign some weights to the different observations that we have. One way of doing that would be to have so-called exponential weights. So we just start with a weight of 1 for the most recent observation, and then the further back in time we go, the less weight we add on it. Have you done this before? Where did you do this? Yes, exponential smoothing. It's essentially the same thing you're doing. There you just calculate a mean value where you weight the observations. Now we can have, you can say, a more flexible function in here. So what we'll do is just to add some weights in there, and then we need to figure out what to do next. Well, we still want to figure out what is a good value of theta. So what we want to do is, for a given structure of the weights, we will just minimize again this function. So we have the same criteria as the usual one, and we can write it on, this is a vector of all the prediction errors. It goes from the most current to all the way backwards in time, and then we have the weights, and then we have the same epsilons or prediction errors again here. Now, we could reformulate this weight matrix as a sigma, uppercase sigma matrix, where we, in the diagonal, have the inverse of what is written there. Can you figure out why I want the inverse there? Or is it too early Friday morning? That's also okay. Yes?
In that way, time 1 be 1, and the farther you get a time
Actually, this value here is larger than 1. So the weight becomes lower because I have lambda to some power here, and lambda is a number that is less than 1. But when I look at the diagonal matrix here, these, you can say, values that correspond to the old observations are larger, because it's 1 divided by a small number is a large number. Have an idea? Yes? It's exactly because it's the inverse that you use when you do the weighted least square. So then you have the inverse of the weights up there in the criteria. So that is exactly what we want to do. We want to kind of get back to something that we sort of know. So we have for the weighted least squares, our model structure, just to recap that first, is that we have some observations, and we get them as X transpose, let's give it a t for some time, on the parameter values plus epsilon t. And what we also have here is that the vector epsilon comes from a normal distribution with 0 mean, and then we write the variance as a scaling factor, lowercase sigma square, times an uppercase sigma. For this setting, we have the theta hat weighted least squares is, as is written up there, x n transpose sigma inverse, which is why I wanted inverse just before, xn, this inverse, xn transpose sigma inverse, and then all the observations y. So that's what we've done so far repeatedly. Or maybe not repeatedly, but at least sometimes. So what is the difference between the weighted least squares and the trend model setting? The difference is that up here, the residuals could be assumed to be having the same structure. Or it could be something different, but we don't have this uppercase sigma in the expectation of the structure of the sigmas. So, per default, we would assume that all observations have the same error structure. Of course, there can be situations where the variance of the signal changes over time. We'll get back to that, at least just a little bit. But that's the one difference to keep in mind here. So the solution to the problem, following what we did last week, is to do a similar structure where you have Fn and Hn. You can calculate that by a sum. That's fairly easy. The only difference from last week is that now we have some lambda to the j power involved. So the whole structure, how to kind of make this work, is the same. We just have to keep track of the lambdas as well. The one thing to keep in mind is, I'll just say it again, when you have the uppercase sigma up there, the diagonal is lambda inverse. I mean, the lambda to the j power inverse. Okay, so the next thing is, and that's where, essentially, that's where this comes into play. Indirectly. And that's the hard part of it. We'll define the memory of the system as the sum of the weights that we use So we take the sum of all the lambdas to the j power from j equals 0 to n minus 1. So what does that give us? Well, we saw the graph before of the decaying weights. I don't know if you remember what is the value of that. Otherwise, it's here. It's the, well, if it's infinite sequence, as long as lambda is less than 1, it's 1 divided by 1 minus lambda. Now it's finite, so it's only 1 minus lambda to the n power divided by 1 minus lambda. So T is a measure of how many effective observations that you actually have. So if T is, say, let's just assume that n is large, then it's easy. Let's assume n is large, and let's say if lambda equals 0.5. Well, 0.5 to a large power, that's 0. So then it's 1 divided by 1 minus lambda. That's 1 divided by a half, that's 2. So if lambda is 0.5, then the t becomes 2. Now if lambda becomes, say, 0.8, again 0.8 to a large power is virtually 0, and 1 minus 0.8 is 0.2. The inverse of that is 5. So you have effectively 5 observations. If you consider it doing just a general linear model, you have the same information as if you have 5 observations, if lambda is equal to 0.8. So that's one thing to keep in mind. But you do have the weights going all the way backwards in time. So all observations have non-zero weight. But the sum of the weights for lambda equals 0.8 is 5. So that also means that we need to make an estimator of sigma. How do we do that? Well, the usual estimator from the weighted least squares is similar to this, but not exactly what is written here. It's the residuals that we have here and there, and we weight them by the weight matrix. That's the same part. But there, in the default weighted least square solution, you divide by n minus p. Here we should divide by t minus p. And this expression is not, it's one of the things that is missing in the book, in my view. And you will need it. And I will show you why you should not use n minus p in a moment. So t has to be greater than p. That's fairly obvious when I just say it. It's the same thing as you had in an exercise last week or the week before. How many observations do you need before you can make an estimate of a general linear model? Well, you need the same number of observations as the number of parameters you have. Otherwise, you cannot do anything. I would say, in practice, you would need a few more, because otherwise you don't have any extra observations, so you don't have any uncertainty left. But the minimum is, say, for a linear regression, is 2. You can fit a straight line to 2 points. We all know it's a perfect fit. So that's what we want to do here. And what you should keep in mind is that it's simply because in the weighted least squares, the weights here is part of the estimate of sigma. It's here you say that the epsilons, it comes from a product of these two, but now we just assume that we have sigma. And that's the reason why we should not divide by n minus p, but the effective weights that we have in here. Now, yes?
I've just lost track of what is p. Is it the number of points you want to estimate?
P is the number of parameters in the model.
Okay.
So for a simple linear regression, you have an intercept and a slope. So p will be 2. Good. So p is, as it was also last week, and is, I wouldn't say always b. In a linear regression related setting, p will be the number of parameters in the model. Okay, so the next thing is, can we do a similar update as we made it last week? For the global model, can we also do that for the local model? Well, you can say it's not that different from last week. I will just, if we go back and look at the expressions that we have here, then we have Fn, which is equal to the sum from j equals 0 to n minus 1 of lambda to the j power f of minus j f transpose of minus j, and we have hn equals to the same, no, sum over the same elements, j equals 0 to n minus 1, and we have also lambda to the j power f of minus j, and then we have y n minus j. So that's the definition of these, and here we are again. It's fairly easy to see this first one here, because all that happens when you increase n is that you have one more term in the sum, and that is the one with lambda, with j being the highest. So when I add something from fn to fn plus 1, the term that I'll get is having the next value of j, which will be then n. So it's lambda to the n power and f minus n, f transpose minus n, as is given here in the top line. The h expression is a little bit more tedious, as it also was when we looked through it last week. But the effective thing is that what we need to do is to shift time. That was what we discussed with the L operator here. It does shift time backwards. And then when we shift this backwards in time, well, we also need to increase the power of lambda. So one step backwards in time, you should also multiply it by lambda to reduce the weight of that. So therefore, the difference between last week and this week is that now there's a lambda here. The most recent observation has weight 1, and it still has weight 1. So there's no difference in the last, after the plus here. That's the same as last week. So the only thing is, whenever we shift time backwards, which we do with the L to the L inverse here, we have to multiply with lambda. All the rest is the same. This is what you're going to do in assignment 1 in one of the further questions. At least that's one way of solving it. And the question is then also, how do you initialize this? The easy thing is just to go with h0 equals 0 and f0 equal to 0, and then just take it away. Now, what should you then do? If you're doing this, there's one thing you should be careful about. If you start with h0 and f0 both equal to 0, and then you start making a for loop from n equals, well, 1 to the number of observations you have, what should you not do? Yes, and you should rely on them as you should update fn and hn, but there's one thing you should not do. What you said is, you can say the correct thing, but it's not the correct reason. Now, you need the first few observations before it makes sense to estimate a linear model. The estimation is what happens when you calculate theta, right? So it's this particular line. These up here you have to calculate each time, but you should only calculate theta hat when you have a sufficient number of observations. That's the point. And now, what is the reason why you need to do that? If you look at F, and you look at only after the first update, what do you have then? Let's just take the simple linear regression model, where f of j equals 1j. That's the simple linear regression model. We can do it locally. And if we then calculate uppercase f of 1, well, we take the 0 that we had before, plus lambda to the n power. Well, we're looking at n here being a 0, so that's a 1, times f of minus 0. Well, that is, I can write it up here. It's f0 plus lambda to the 0 power f of minus 0, f of minus 0 transpose. And if we look at this, what do we have? This is a matrix of zeros plus 1 times a matrix here of 1, 0 times the same as a row vector, 1, 0. So the value that we get out here is a matrix 1, 0, 0, 0. Right? Can you invert that? No. Well, then you cannot solve this. When you then add one more observation, then what you will have here is a 1 and a 1 and a 1. And all of a sudden, things are a little bit more enlightening. So that's the reason why you cannot solve it, because you cannot invert that matrix. It doesn't have full rank. Yes?
Also because you need a burn-in period before the answer is meaningful?
That's the other thing. One thing is that you can do things, another thing is, does it actually make sense? I mean, can you rely on it? But I'll show you that later, how that actually works, because I will just start from the start, and whenever I can do things, I will try to do it, and then you'll see what happens. Now, this may not be so useful nowadays that computing power is very cheap. But what we discussed is that lambda to the n power is usually, when n becomes large, it's a small number. And depending on what you have as a function here, fn, now for the linear part here, that part there, what is that? F of minus n, f of minus n transpose equals, well, we have the definition of f there. So what we end up having is a matrix where you have a 1 and you have an n square down there, and then you would have a minus n and a minus n. When you multiply this with lambda to the n power, then the question is, how fast does this grow relative to how fast does lambda to the n power decrease? And lambda to the n power decreases fast. So therefore, you can do this where you say you have a stationary f after a long period of time. You can calculate what it is in the limit, and then you can make another update where you don't have to keep track of h and f, but you just have to keep track of the previous lambda estimate. You move it forward in time, and then you make an update that it comes from what is the observation and what is the prediction that you made for that with that weight matrix. I won't go through the derivation of this. If you like, you can have it as an exercise. But I think in practice, the computational saving that you get by doing this up here is sufficient for most settings. Some of you asked me last week, well, where is the big saving in doing this relative to doing, you can say, just the full model estimate every time? Well, how many operations? Say n is 100. What you need to do here is, this is, say, for the linear model here that we have here, this is a 2 by 2 matrix. It's fairly easy to construct a 2 by 2 matrix and land it to the n power. I mean, if you wanted to, you can save the previous lambda to the n minus 1 power, and you just have to multiply two numbers. That's also fairly easy. The hard part is that you have to invert a 2 by 2 matrix, because all you have here is L inverse you will pre-calculate, and the rest is just a small multiplication. So the number of operations here goes with the dimension of the system. In this case, it goes with p equals 2. If you go back and want to do the full model, well, then you have the full list of observations at every time. So you have, say, 100 observations, and you need to calculate this fella down here. You have 100 observations, so this matrix here, X, has 100 rows. Likewise there. And sigma inverse, well, you can say that you only have numbers in diagonal, so you don't need to do that. But you have all the 100 times all the 100 rows and columns here. And then when 100 becomes 10,000, well, then you have 10,000 rows there. So it's the calculation of what you have in here, and likewise the calculation of x transpose y, that part here. That is what takes time. So all of a sudden here, in this system here, the number of operations scales with the number of observations. Whereas in this setting here, it only scales with the dimension of the parameter vector. Whenever you go forward in time, the calculation is always the same. Here, whenever you get a new observation, if you want to redo it this way, you have to recalculate everything. It actually means that the number of observations scales with the number of observations to, I think, the second power or third power. Whereas up here, it's invariant. So that's, you can say, the motivation in a real-time system. When you're just sitting doing things on your computer, post hoc, it doesn't matter so much, because you can easily calculate this for any, real-time system. But if you have something that is going to be accurate, you have to deliver things in actual real time. You have to consider how many operations do you need to do to get the next result. And that's why I like this formulation up here. So now, just going for a small example. So what we have, let's just say 6 observations here. And then we have first we'll just go back to the global linear trend model. And with this formulation here, we have the observations. We have the design matrix here with 6 rows. And, well, here we'll just solve it without doing the iterative updates because it's so small. And we get estimated parameters here. So remember that the first element in theta here is representing the mean value at time 6, and the second element here gives us the slope. So whenever we want to make a prediction one step ahead, what we have to do is just to add those two numbers, and we have a prediction. We can also write it in this form. So the line is giving as the reference value plus the slope times how much forward and backward in time do you go relative to time 6. And we can make an estimator here. It's the global estimator, so we'll use n minus 2 as our estimator for sigma. And the prediction error is just as we did it last week. I'll write it up because we'll need it a little bit later. How it is. So the variance of, let me write it, the variance of the L-step prediction relative to time n is equal to our estimator of sigma hat times 1 plus F transpose of L, Fn inverse, and then F of L, like that. That's the estimator that we have for the prediction error. So this is the estimate that we want to use whenever we're going to say something about a future value. So what does that mean? We have the same equations here as we did last time. We have this for the one-step prediction. It's just the sum of the intercept and the slope. And we have a variance here that is, of course, slightly larger than the variance up there. And we can make it into a prediction interval. And if we add the fitted line to the graph, we have it here. And I added the prediction interval there. Now, what happens is that we then get the next observation at time 7. We do the update of F. We can see that it has this structure. It's a sum of these. So what you have here is the sum, is actually n. And you have the sum minus the sum of the number from 1 to n, and the sum of n squared. H, of course, involves the observation, and we can get a new estimate. If we now take, this was what we had before, given t equals 6, and now we got the observation of 3.5 here, and then we can update. We actually saw that the observation that we got was just outside the 90% interval. That's okay. We should expect 10% of observations to be outside. So we make an update at time 7, and of course we could use this to predict to time 8, and we could continue like that. That is what I want you to do in the exercise or the assignment. Now, what we wanted to do is to do this locally. So we'll do the same thing. Calculate F6. We'll just pre-calculate it to get started. We'll just say that we will have this burn-in period, as was mentioned. So we won't care so much about making a nice, efficient way of calculating the first few. We'll just do that. And when we have calculated F6 and H6, we will get our first estimate. And from there on, when we update things, then we can do it using the update algorithms that we just shown before. You can see the estimate here is not the same, but it's close. The estimate for sigma. Sigma is almost the same here, by coincidence is not constructed. And the variance is also similar. I think it's slightly larger than it was just before. Let's go back. Here, so 0.62 and 0.45 up there. So 0.45 and 0.62 was the reference value. So they are not unexpectedly slightly larger because we forgot part of the information. So we have less information, which means that we are less certain. That intuitively it makes somewhat sense. Of course, it also depends on what is the true model. Here the true model is probably a linear approximation is good. If a linear approximation was not so good, it could be the other way around, that doing the local model would give you a lower prediction error. And if we have the global trend model to predict time 7, this is the line from before, and the local model gives you almost the same prediction. And the prediction interval is slightly lower because of the F being different. Now comes the tricky part. What to use as an estimator of sigma? I've done one thing so far. What I've done is to use this estimator. So what does that do? It places us at the most recent point in time and gives us an estimate where you only use the most recent observations. Well, you use all observations, but effectively you're only using the most recent ones because all the older observations have a small weight depending on what lambda is, of course. So this is one way of calculating sigma. If you have a very noisy signal, or if your lambda is fairly low, you do not have that many observations. So this may not be the nicest thing to do. It works. It works okay. But let me just show you the difference between using t here and using n, because that's the expression that you will find if you look around in the book and found the page for the weighted least squares and say, that's about the same thing. You should keep in mind there is a difference in the interpretation of the error, which is why you should not use n there. Oops. So what I've done is that I've made a small script here. I won't show all of it because that will solve the assignment as well. So there's a few things that are kind of saved somewhere else. So it won't be complete. So I will just say for now that I'll have a transient of 2 points because that's what I need before I can invert the matrix. But I mean, in a more realistic setting, you have a larger transient. But I want to show you how it goes. I'll create a time vector and have a true theta vector and a true standard deviation that I'll use throughout the data. I'll create my design matrix, and then I will get some random normal values, one for each time point, and with a mean value of x theta and the given standard deviation, and plot it. So that's the data that we're looking at. You can say this is a nice, well-behaved case where the true model is a linear model. But if we cannot make it work there, it won't work otherwise. Okay. Now I have my local linear model running through this. And I need to change my session. Bang. That's the code I have in another tab up here. Basically, it just runs what we just did. You make a prediction, then you get the observation, and you make the update, step forward in time, make a prediction, get the observation, make an update. Going through the entire system, that's what you get. If I do now you have to look into how to estimate sigma. First, I will look into, we have the observations y and y pred. I guess you can assume that the predictions that I made. So these are the prediction errors, and I will only look at those that are not to be excluded, and how many there were. Then I get an estimate, remembering that the true value was 1.5. It's not too far away, but it's not close either. It's a bit too big, right? Now, first let's look at how many effective observations do we have. So I'll calculate the 1 minus lambda to the current time divided by 1 minus lambda. It looks like this. So I used, can you guess what the lambda is that I used from this? One minus that. 0.9 exactly. So I end up having 10 effective degrees of freedom, and in the long run, when n is large, t goes to 1 minus lambda for n going to infinity. That's the nice way of writing it. I did calculate it up here with the right thing. So what is the effective after one observation? Well, I have one observation. After two, I have a little bit less than 2 because I've weighted down the first one. So I only get 90% of weight from that one. But after, say, around 50, I'm very close to just have 10 all the way out. But there is a burn-in phase. And if lambda was lower, the burn-in phase would be slower, because it's the lambda to the n power that is kind of taken out. Now, the next thing is that I will compare the two different estimators. The one that I have here, where t minus p is equals to 2, and also using n. So what is happening here? If you look at it, the black points are at each point in time. I made the estimate given by the errors, sigma inverse times the errors, divided by t minus p, and the red one, the only difference is n minus p. Can you see what happens? Initially, as I said, I want to get back to the models and the estimates are very bad. They are way too high relative to what to expect and what we wanted it to be, but we're not surprised. Already when you get to, say, 30 or so, using t minus p stabilizes around the true value, jumps a little bit up and down, because we only have effective 10 observations. So it is expected to be a little bit uncertain doing this. And I just added a green line to show the true line. But the red one here, what is happening? It goes to 0. Because n is just increasing, increasing, and increasing. Whereas the E transpose, or the epsilon transpose, sigma epsilon, you have new observations coming all the time. You know that the F matrix up there, Fn, converges to stationary matrix. It's that one that you invert. So you don't have any more information coming as time is progressing. It's the same information that you have but you just assume that you have more and more of information each time. So when you have the locally weighted model, don't divide by n minus p. Now, another approach, this is an in-sample estimator, because we looked at the theta that we estimated and calculate backwards in time what is the estimate. An alternative, we can also do it out of sample. Sort of what we did last week. For the simple exponential smoothing, what we did was to look at what was the sum of squared prediction errors. Why not use that instead? We take y minus the prediction of y one step earlier. And again, we'll keep track of the first initial ones. Look at the cumulative sum of those. Then I set them to NA. That's just a trick to make the plot look nice. And then I will add that as a line. And update the legend. So this is a running mean value for the sigma estimator, where I just look at all the one-step prediction errors. I take the cumulative sum of all the one-step prediction errors and I divide by the number of elements in that sum. So what I have here, what I call running mean, what I have there is the sum from, in this case, t equals to 3. And now I use a lowercase n to say it's not to the end of time. T equals to n. Using n observations. What I have here is yt minus y hat t given t minus 1 square. And then I divide by n minus 2 because I left 2 observations out. So this I can do. I only keep, I do prediction errors here. This is actually not the optimal thing. So what I do here is I get a global estimator. The black and the red lines, or the black dots there, are local estimates. The cyan line here is a global, assuming that the sigma is not changing over time. Yes?
Uppercase or lowercase n in the denominator?
That should be lowercase as well. Thank you. Just because uppercase n is kind of the full length of the series, you just want to use something different. Thank you for saying that. Now, is this good? I mean, it looks more consistent, but it's actually the best thing we can do. It's one of those leading questions where the answer is, it's not the best thing we can do, right? So what do we know about this prediction error? When you make a one-step prediction, do we expect that to have variance sigma? When we have a linear regression model, we have a few observations. We fitted a line. We know that we have this trumpet-shaped prediction error thingy, and we are now going to make a prediction. What is happening out here? Does that have variance sigma or something different? go back to the slide here. When we do the one-step prediction, we don't have variance sigma. This is the estimated sigma we have. But that's not the variance that we have for the prediction error, because we have to take the uncertainty on the parameters into account. That is the reason why I wrote that expression there. It's just next to where we're going to use it. So far, we assumed that there's no contribution from the uncertainty of the parameters when we just did this. If we use this here as denominator as well for each individual term, that's the tricky one. So what we will use here is the sum. I will just write it. I don't know if I can write up here. Oops. I'll write it here. So the alternative down here where we correct for prediction error, prediction variance, is quite similar to what we have up here. I'll take the 1 divided by n minus 2 outside, and then I have the sum from t equals 3 to lowercase n, and then I have the same yt minus y hat t given t minus 1 square, but then at each point in time I have to divide by this, and this will become a scalar number. So I can just write it, and we're looking at one-step prediction errors, so it's 1 plus f of 1 transpose, and then I need the f inverse, and the index for this f here is ft, uppercase ft inverse, and then it's lowercase f one-step prediction error again. So if we use this instead and go back, I take the prediction errors that we had up here, and I divide it by the scale of the prediction error, which is a sequence of those numbers down there. Again, I put the first ones to 0, as I'm not going to use them. Do the cumulative sum. Then I get this. So the magenta line here is the weighted running mean. And if you look at it, you only need a few observations before it's actually very close to the true value. I think that's the important part. It's actually quite consistent, this estimator. So what I propose is that you have two choices. Either you use a black dots to get a local estimate, or you do what is the magenta line there to get a global estimate. But it depends a lot on the situation. You can see the black one there, it jumps up by, say, a factor of 2 away from the true value, but it's consistently near the true value. Whereas the magenta line stays quite close to it, but it's only good if it's a good approximation to say that sigma does not change over time. So that's the take-home thing. Yes?
Why does it in the denominator there say F1? I mean, what's special about F1?
F1 because it's one-step prediction.
Okay.
Yes, so it's a one-step prediction error that we're looking at. And if we look at those, the Pret scale, so what is this denominator here, what is that actually? I just plotted it here. Initially it's large, and then it goes down. And if you just look at the last number, it's 1.21. So it's just a scaling when you get a little bit into it, but I do it for every single element. If you disregard the first 50 or so, well, that's what you have. You have 21% that you did not take care of if you did this relative to this down here. Now, this was just doing this once. So I showed you the graph here where I did this for just one simulation of 300 observations from this process. If I instead simulate this 200 times, I wrapped that in a function behind the scene, and then I look at the first. Actually, I want to make the plot down here instead. That's nicer. So what I have plotted here is I normalize, as you can see here, with the true standard deviation. And I packed them so I have 300, 300, and 300. Let me add the legend now. So I have the weighted prediction error. That's the one that was magenta just before. That's the one I like the most. And what I have shown here are quantiles representing, you can see it up here. I use the quantile function, and I use the maximum, the upper quartile, the median, lower quartile, and the minimum value at each point in time of those 200 observations. So here, this corresponds to having 200 magenta lines. At any point in time, I sort them and look at the quartiles. What I'm caring most about is the inner quartile range, so what is in between the two dashed lines. The minimum and maximum are just there to see, well, how bad can it actually go. If I then add the unweighted, this is this one up here. When I add this, well, we see that it is consistently above the black one because we did not divide by this 1.21-ish. Initially, the factor is larger, which you can also see. If you go back to the slide before, you can see initially the weighting factor is larger, or the scaling factor. But the black one very quickly goes in and gets close to the true value. And now it becomes a little bit busy because now I add one more thing that I've seen students use. Not that I suggested, but just to show what happens. If you take the sum of not this, but if you take the sum of let me wipe that out. If you take the sum of yt and the updated yt, so you have the observations yt minus y hat t given t. So that's the estimate that you have of where you are after you update it with the observation. So for the local trend model, it will be the first element in theta, generally. So I can make the sum of this square. Again, t equals 3 to lowercase n, and I divide by n minus 3. If I do this, I get something that is consistently too low, because I do something that is not out of sample. I do something where I actually use the last observation to reduce this error. So it's not a good estimator. But just to show that you can come up with many different algorithms that are not performing that well. But you should also see that, I mean, some of the blue ones and red ones are actually close to the true value, but they are just consistently off to one side or the other. So if I, instead of plotting what I plotted before, just plot what is the fraction of these 200 simulations that are below the true value. Then when I use the unweighted, I get roughly 10%. If I use the weighted down here, I get quite close to 50%, not exactly, but I get very soon I get to around 60% in this case. And if I use the one with the in-sample problem here, I get around 100%. I could have done that, but I did not try to do the same skill score with this one for the 200 cases. It will just be another graph to add on top. It will be consistently a little bit too high, but that's how life is. I know this is a little bit complicated, and I think now is a good time for a break. So let's take a break until 10 minutes past.